Thank you all so much for being here today for my talk about the minds of machines. So this is not a workshop. There's not going to be a lot of interactive content, but there are opportunities for audience participation. And I would like to get a feel for who all of you are. So could you please raise your hand if you build or want to build AI systems to solve problems? All right. And for those of you who are not interested in building them, who here is interested in using AI systems that maybe somebody else built to solve problems? Okay, perfect, you are in the right place. This talk is for you because this is a talk about AI going wrong and the things that you need to do as someone who is either building a system or deploying a system to make sure that you're using it in a way that's going to be helpful rather than harmful to people. So first off, this is not a talk about killer robots. When I say that AI goes wrong, there are a lot of stories about evil computers, and evil computers do things like blowing people up or shooting them or launching them into space or locking them in pods, and it makes people very, very frightened of AI. I have wonderful news for all of you. There are precisely 0 evil computers in the world today. No evil computers at all. Good job, everyone. The bad news is that AI can still go wrong. And what does that mean? It means that when artificial intelligence systems or any kind of computer systems cause harm to people, and it can be very serious harm, we live in the 21st century, people have been killed by AI systems. What's happening is a mistake. What's happening is an accident where the system is not performing in the way that people intended for it to perform. And so it is the responsibility of people like me and people like all of you who like AI and want to use AI to make sure that we're going to avoid the kinds of problems that I'm going to talk about today. And to start with, let's talk a little bit about what artificial intelligence is. There are 2 sort of broad areas of study in AI. One is talking about artificial intelligence in the same way you talk about any other simulation model of a real-world system. So for example, you can simulate the weather, you can simulate the solar system, you can simulate a building, and you can also simulate a brain. So one thing that you can use artificial intelligence for is as a well-controlled system that you use to try to understand, for example, how the brain functions or even how things like ideas function. That's not what most people mean. Most people who talk about artificial intelligence are talking about the second thing, which is how do I enable a computer to do something that previously only people did, because it requires you to think. And the problem with this definition, which is the one that I spend all of my time working with, by the way, is that it's a moving target. So every time we enable a computer to do something that people used to be able to do before and only people used to be able to do, we downgrade it and we say, oh, that's something that computers do now. So I remember when I was a kid, people were saying, oh, well, computers can't beat people at chess. So that means that chess is a sign of intelligence. And then as soon as computers started beating people at chess, they said, oh, well, Go is actually a sign of intelligence. Computers can play chess. And so this is why I'm going to be talking about a number of sort of older examples of AI that are not the current most trendy methods. The current most trendy methods are soon to be the things that computers have always been able to do for people who are younger than me. So let's see if I can do this. All right. So this talk is not a talk about specific AI algorithms. I am going to be talking a little bit about specific algorithms, in particular machine learning algorithms, which are what I typically work with. But this is a talk about AI systems. So an AI algorithm is something that lives in a computer. It's something that you work with in a lab. It's something that if you're at a university, you write papers about. It's not something that anyone is necessarily using for anything. An AI system is what happens when you take one of these algorithms and you put it out in the real world where it is interacting with people. It's potentially being used by people, it's potentially making decisions about people, but all of a sudden, its actions and its accuracy have real world consequences. And one of the most common anti-patterns, if you will, for AI, which is one of the most common system design issues that comes up is that when a human being sees a computer doing something that humans also do, they assume that the computer is like a human. And this makes a lot of sense. We're very accustomed to dealing with other intelligent beings that are like us because we're social. We interact with each other. Most of the time, when I meet something that plays checkers, that something is another person. And so it's safe to assume that it's going to play checkers, say, or chess, or drive a car, or fly an airplane the way that I do, or hopefully fly an airplane better than I do, because I'm not very good at that. So if computers don't think like people, how do computers actually think? Well, the answer is that computers think like pocket calculators, just bigger, stronger, and faster. And this is because every computer that you encounter, from the computer in your cell phone, to a laptop, to a supercomputer in a government lab, all of these machines are the direct line descendants of fancy calculators from the 30s and 40s. And that means that they're really good at things that calculators can do. So for example, they're really good at arithmetic. They're much better than we are. If anyone in this room could do 10,000 floating point calculations per second, that would be very impressive. For computers, it's pathetic. So second thing that computers do better than people is memorization. Imagine YouTube. If I took a video recording of my birthday party and I upload it, within a week I will have forgotten most of what happened at my birthday party, but YouTube will remember forever, and pretty much flawlessly forever. You can fit the entire Library of Congress onto a computer, a very large computer, and you can search it and you can recall anything from the Library of Congress perfectly that will not fit in a human being's head. It's not even something that we can compete with if we allow ourselves to use the luxury of paper to write things down. Computers are much, much better at memorization and retrieval than human beings are. Finally, computers are really, really good at doing what they're told. So who here has programmed computers? All right, who here has had the experience of the computer doing what you told it to do, which was different from what you wanted? Yep, that's pretty much everybody. It's actually very frustrating. They don't do what you want, they do what you ask for. And typically when computers do things we don't want, it's because we very foolishly ask them to do so. So computers are also very good at a couple of other things that are related to these skills. For example, computers are very good at talking to other computers. Computers are also very good at multitasking, specifically task switching, where they can do one math problem and then another math problem and then go back to the first one without losing information. People can't do that. Anytime you've tried to use your cell phone and practice any other activity, you've had the experience of how humans cannot do that very well. But other than those things, computers are not as good as people at most things. Computers are inflexible. Computers lack initiative. So this is why there are no evil computers. Computers can't want to do evil things because computers can't want anything. Computers are bad at dealing with novelty. They don't know what to do in a situation that they haven't encountered before. Computers are not good at creativity. There's a lot of talk in the media in particular about computers doing things that they haven't been programmed to do. And this is considered to be one of the definitions of AI. It's misleading. Computers are doing exactly what they're programmed to do, but the outcomes of those programs are not always anticipated. So when you think about a computer doing something that a person does, what it's really doing is really fast math and really good memorization for every computer that we have today. And that's typically not how people are doing it. All right, so before you deploy an AI system, which I assume everybody in this room wants to do at some point, here are the 3 questions that I want you to ask and hopefully be able to answer before you decide that you're going to send the computer out into the world to interact with human beings. The first is, how is the computer accomplishing the task that you've set for it? And you have to recognize that it's not doing it the same way that a person would do it. We're going to get into a few detailed examples of how computers do the same thing people are doing, but in a very different way, and why that's important. Second, because you understand how it's doing things, you're going to understand how it's going to make mistakes. And this is, again, very, very important because computers don't make the same kinds of mistakes that people do. And again, the number one cause that I see of AI causing harm in the world is people not anticipating the kinds of mistakes that the computer is going to make. And finally, and most importantly, what are the consequences of a mistake? It is not a coincidence that the most common applications of AI that we hear about are in environments like playing games, video games or board games, and advertising. And that's because the consequences of mistakes in these contexts are very, very low. So what? You lost a Go game. So what? You showed somebody an ad for something and they didn't click it. It doesn't really matter that much. And that means that people can rapidly experiment. They can make a lot of mistakes. They can deploy really bad algorithms and it doesn't hurt anybody. But as we're transitioning into using AI in more consequential application areas, which we're already doing, into things like transportation, self-driving cars, into things like heavy industry and manufacturing, which is where I work, into domains like medicine, those mistakes matter. And so you need to understand what they look like, and you need to figure out how to mitigate them. All right, so as my first example of the level of information that you have to get about an AI system before you want to put it out into the world, we're going to go with a classic, which is an AI checkers playing program, which was called Chinook. So Chinook was an AI program that was competitive in actually human tournaments in checkers in the mid-90s. It was the first AI program to compete in a human world championship and win a game against a human world champion. When you think about things like Deep Blue versus Garry Kasparov or the AlphaGo tournaments, those were all exhibition matches. Chinook was actually playing for all the marbles. It was competing for the human championship. And the same team that developed this program actually solved checkers in the year 2007, which means that it is now possible to build a completely unbeatable checkers playing program. We're not going to be talking about that version. We're going to be talking about back in 1994 when the computer was very, very good, but not impossible to defeat. All right. So in case you're not familiar with checkers, it's also called drafts in much of the world. It's a game that's played on an 8x8 board, similar to chess. Each player has 12 pieces. Pieces move diagonally forward, and the goal is to prevent your opponent from moving. This is usually done by capturing all their pieces. Captures take place diagonally. So my black piece just captured my white piece. If you have a capture available, you are required to make it. There are a couple of additional rules, such as pieces can move backwards if you make it all the way to the far end of the board. But the idea is that it's a fairly simple game. It's a direct line descendant of games played thousands of years ago in Egypt and Mesopotamia, and much, much simpler than things like chess and Go, both because it has fewer pieces, fewer movement sets than something like chess, and it has vastly fewer board positions than something like Go. Checkers still has more than 2 billion viable board positions. So it is still a respectably complex game that was being addressed in the 90s. So let's think about how a human plays checkers versus how a machine plays checkers. And so the machine is obviously going to be represented by Chinook. Humans are represented by Dr. Marion Tinsley, who is a math professor and possibly the greatest human checkers player to ever live. The computer Chinook beat him in 2 games in tournament play, which was once more than any human ever defeated him. He was truly astonishing. Unfortunately, he passed away before Chinook had sort of fully realized its potential, but he was a big supporter of the project. So the game of checkers and most board games have 3 phases, depending on the level of complexity, essentially, of the board. So how many positions can the board have? And it goes from a low complexity state, called the opening, to a high complexity state, which is the mid-game, to another low complexity state, which is the end game, which is when most of the pieces are gone. So how does a human play the opening in checkers? Well, when you're a tournament level player in checkers, chess, or Go, any of the classic board games, what you do is you study books of openings. So there aren't that many opening moves. I think that there's exactly 8 7 ways you can open a game, and then the second move, there's 49 board positions, but some of them don't make any sense. So people study games of moves, and then when you enter a tournament game, you start out by playing a sequence of moves. Your opponent is probably also familiar with the sequence of moves, so you're going to play in a predetermined fashion up until the mid-game. So humans memorize opening moves using imperfect human memory. The computer memorizes opening moves using perfect computer memory. So the only weakness the computer has is if it hasn't ever seen a particular opening before. And this was actually one of the ways that Chinook advanced in tournament play. It started out with a very weak opening book. It just didn't have very many lines of play available to it, and then it got stronger and stronger as more and more openings were built into it. People understood how Chinook's opening book worked, and in particular, they knew that it had a weak opening book to start. So tournament players who were competing against the computer were able to defeat the computer by playing obscure openings. And so even without being computer scientists, they understood it well enough to be able to beat it based on how they knew it had to be playing. All right, the second stage of play is the mid-game. And this is where things get really interesting. And this is, by the way, where most of the action is in contemporary games playing programs such as AlphaGo and AlphaGo Zero. In the mid-game, there's a pretty good chance that you're going to end up in a board position that hasn't been seen before. And you need to be able to figure out what to do next. The way that a human does this is they think about what they want their next move to be, they imagine their opponent's possible responses, and they sort of play out a sequence in their head. And we know that humans can evaluate 1 to 2 board positions per second when they're playing at a very high level. And so you can imagine if they're taking 30 seconds to a minute per move, they are not actually considering very many moves, very many lines of play. So what humans do that is mysterious and which we have never really been able to teach computers how to do is we throw out tens of thousands of moves without thinking about them. We can just look at the board and without thinking it through say, that's horrible, don't do that. And almost instantaneously dismiss most potential lines of play. Computers can't do that. Computers have to try absolutely everything. So back during Chinook's day, a computer could evaluate, let's say, 10,000 board positions per second. By Deep Blue, I think it was 100,000 board positions per second. It's much higher now. So instead of just instantly throwing out stupid moves that were never going to work, the computer tries them all. And it tries as many as it can before it has to make its move. There's a lot of work that goes into an intelligent scoring system for trying to appreciate which lines of play are going to be successful and which ones aren't. This can be done with machine learning. But for the original version of Chinook, it wasn't. So this is a segment where humans are able to do something typically more successfully than the computer was. So when Chinook was playing past its opening book, people knew about how far ahead it could look. So say 7 moves ahead to 10 moves ahead. And they could pursue lines of play where it wasn't clear that Chinook was in trouble until it was already too late. And so this was how people were able to understand how the computer was playing and were able to beat it. And then we get to the really interesting part, the endgame. So people pursue endgames in similar ways to how they pursue the opening, which is there are not very many pieces on the board. There are patterns that you can recognize, and so people will study endgames, and then they will play off of endgames that they've seen before. That's not how the computer does it. Chinook had, by the end of its tournament play, a comprehensive endgame database up to 10 pieces on the board, which means for any combination of 10 pieces on the board, it had played every possible game with those 10 pieces, and it remembered the outcome, and it remembered what it had to do to win, if it could win. It remembered if it was not possible for it to win, if it was guaranteed a draw, and it remembered if it was guaranteed a loss. So this is not how people do it. This is holding billions, potentially, of games in memory and being able to look them up and play them back precisely. Once you made it to the end game, if Chinook could win, if it wasn't already in a guaranteed loss, Chinook would win. You cannot beat the computer at memorization. You had to beat it before it reached that point. And when the game of checkers was ultimately solved, the way it was solved was by getting rid of this point. They basically built out the opening book until it met the endgame database. And so the computer was playing purely off of memorization. And that's why you can't necessarily beat a computer at checkers anymore. This is also the place where the most interesting things could happen, because this is where the computer was playing in a fundamentally different way than a human player was. A human player would dismiss large suites of moves out of hand as a factor of experience, and Chinook would try absolutely everything. And sometimes trying absolutely everything led to unexpected positive outcomes. And so what did it feel like for a human being playing against this machine? Just so you know how it worked, Chinook was usually not co-located on a computer with the game. It was usually being sent messages over a modem, and then it would report moves back. And so there was a human being sitting across from the other player who would then play all of Chinook's moves. And people would talk about the machine like it was a person. So when Chinook was playing in this mid-game mode where it was trying absolutely everything, and sometimes it found unusual and counterintuitive lines of play, people said that it was creative. People said it was an exciting player. It wasn't creative. It was trying absolutely everything, and every so often it would just stumble onto something no one had tried before. Similarly, after the opening book got stronger, Chinook became a more conventional player because it was playing off of memorization, known lines of play that the other players knew. This happened to be after it had won the man-machine checkers championship, and people said that Chinook was scared to lose, that it had become a conservative player because it was afraid to lose its crown. Chinook was not afraid. Chinook knew no fear and no joy. But it was interesting because the people who controlled Chinook changed what they wanted Chinook to do. So they started out saying, let's build a checkers program that's just going to dominate people in checkers, an unbeatable checkers program. And when they started getting this feedback, these people, by the way, had been embedded in the checkers community for years and years by this point. They said, let's change the program so that it's fun to play. Let's change it so that it is enriching the experience of checkers, so it's going to do more unexpected things. And they got rid of the opening book for certain games, and they played exclusively in the tree search regime so that it would be fun for people. So that's an example of people modifying the way that an AI program works to try and make it more rewarding for a human community. All right, so the reason I chose Chinook as an example is because it's pretty easy to answer this first level of questions, this first question at the level that you need to be able to predict how the computer is going to behave under different circumstances. Lots and lots of checkers players who had never programmed a computer in their life knew how to beat Chinook when Chinook was weak. They took advantage of when it had a weak opening book, they'd play unusual openings. When it moved into the mid-game, they would know that they could play certain established lines of play that Chinook would not recognize, and it would take long enough to develop that they could defeat the game. And they knew that if they made it to the end game and Chinook had a way to win, it would win. You had to beat it before the end game. And I've told you all of that without explaining how the algorithms worked, how the database algorithm for the end game worked, how the development of the end game database worked, how the tree search and scoring worked. So when I say you have to understand how algorithms work, this is the level you have to get to. So this is not something that is just for AI scientists, computer scientists, mathematicians. You can understand AI algorithms well enough to use them effectively if you even have this sort of high-level understanding of how they work. And as I mentioned, people understood it well enough to know what mistakes it would make. And in tournament play, they took advantage of this, and they would use its tendencies to defeat it. And finally, what are the consequences of a mistake? Well, you lose a checkers game. This is the last low-consequence application that we are going to discuss in this talk. But again, this is why AI research took place in places like checkers and board games and video games, because you can afford to make mistakes in ways that you can't with other kinds of systems. All right, so you could say quite fairly that the example I gave you before is not a good example of so-called modern AI. So it wasn't learning from data in its tournament days, which even more contemporary games playing programs do. It certainly was not using any kinds of neural networks, and neural networks are very trendy right now. So let's talk about the kinds of mistakes that neural networks make. All right, so A number of researchers really did this, but we'll pretend that I did this. I've trained a neural network, and its job is to distinguish wolves from dogs. And specifically, I'm trying to distinguish wolves from huskies, which are a rather wolf-like breed of dog. So let's say I trained my algorithm, and I did all the things you're supposed to do. I held out a test set, and this is the results of running my algorithm on my test set. So you can see that for my wolves, it's getting 4 out of 5 correct. For my dogs, it's getting 4 out of 5 correct. So 80% accuracy. And let's say 80% accuracy is perfectly fine for my application. Raise your hand if you think that my AI algorithm is doing a good job telling dogs from wolves. All right. Raise your hand if you don't think it's doing a good job. Okay, put your hand down if you only think that because you think it's a trick question in a talk. All right, okay, so you still have your hand up. What do you think it's doing wrong? But first, have you read the paper that this is from? All right, then what do you think it's doing wrong?
In my opinion, I think the photos are so much near. It's very similar. It's hard to distinguish between wolf and husky, even for humans.
It is?
So this is using a neural network, you will have a lot of error mistakes.
Mm-hmm.
And you need to make it more effective, a very, very large database, and sometimes that's not happening.
Mm-hmm. Well, let's say you're absolutely right, by the way. This is a challenging problem. If I wanted it to be easy, I'd have like Cocker Spaniels versus wolves. There was another hand up back there. What do you think it's doing wrong?
So, my initial thoughts were, it's a naive mistake with training data sets.
Mm-hmm.
Sometimes you recognize that other stuff on the picture.
Mm-hmm.
Initial object. So here I think it's the voice.
You think it's seeing the collar?
Yeah, collar.
Yep.
On the face shape. I think it's mainly the collar.
You are on the exact right track. It's recognizing something other than what the animal is. What do you think it is? It's the snow. So what these researchers did, this is an excellent paper, by the way, and it's about explainable AI and how do we help people understand what AI systems are doing. They trained a classifier on dogs and wolves, but every single wolf was standing on snow, and every single dog wasn't. And so that classifier was distinguishing between snow and not snow, or more specifically, between a light-colored foreground and a dark-colored foreground. So if we gave it this picture, it would say that that is a picture of a wolf, which is, of course, not what that is. But if you think about it, the way that they were actually, let's see if I can get it to go back. There we go. They weren't doing this because they wanted to distinguish wolves from dogs. They were doing this because they wanted to understand how people would interpret the results of this algorithm. So they showed people a slide very much like this one, people who had just taken a machine learning class and were being experimented on, so they should be on their guard. And 30 to 40% of them thought that the algorithm was doing a pretty good job distinguishing dogs from wolves. And that's because if you showed a human a bunch of pictures of dogs and a bunch of pictures of wolves, they would automatically try to classify the subject of the photograph. And they might do it incorrectly, so they might say, oh, well, dogs have collars, wolves don't have collars. But they'd definitely be looking at the animal in the photo. Children would be looking at the animal in the photo. No human is going to say white, green, blue, brown. But computers do. And computers do that because they're looking for any kind of similarity in data sets, not the kinds of similarities that our brains are designed to detect. So this, again, low consequence application. Not just that, it's a trick that a bunch of professors played on graduate students. There is an entire field of research, which if you are interested in neural networks, is called adversarial examples, which is basically finding a way to fool a computer that would never fool a human being. So this is a paper from last year where they were actually studying real-world adversarial examples. So lots of adversarial examples, you're manipulating a file. So you're just changing the image in the computer. A human might not even be able to see it. These people actually put tape on stop signs and took pictures of it, and they were able to convince a computer that this is a speed limit 45 sign with that tape. So I cannot tell you how that algorithm is classifying stop signs versus speed limit signs. I can tell you a lot of things it's not doing. It's not looking at shape. It's not looking at color. It's not looking at the word stop. It's looking at something that's related to these little pieces of tape, which is not ever what a human being would be looking at. And so this is one of the extraordinary challenges of working with deep neural nets and the high-dimensional modern forms of machine learning. It's really hard to understand what they're thinking. We know they don't think like us, but it's really hard to figure out what kinds of mistakes they're going to make, because they do not make the kinds of mistakes that a person would. They make really, really weird mistakes. And this is something that, again, it's an active area of research. It's something people are trying to understand better. But it's something that you have to think about anytime you're using computer vision in a high-consequence context. Because, again, they're going to screw up in ways that don't make any sense at all. All right. On to real-world examples. Maybe. There we go. Okay. So now we're going to talk about actual AI systems that were deployed and caused problems in the world. So this example is from 1970. St. George's Hospital Medical School in London had a problem that all schools would love to have. More people wanted to attend than they could afford to accept. And so they used a human screening process where humans would review every single application, and then they would select a sample of those applications based on the most highly qualified applicants who they'd bring in for an interview. And this was, they felt, not efficient. It was taking up a lot of human time. It wasn't necessarily fair, so they taught a computer how to do it. So they built a classification algorithm based on applications that were accepted and applications that were not accepted, and then they used that to screen out 75% of the applications they were sent. So 75% of the applications they were sent were never seen by a human being. What could possibly have gone wrong? Any thoughts? Yes? Well, they didn't kill anybody. This was just letting them into medical school. They didn't get to be doctors right away. But yes.
I think it could have a certain bias towards, for example, your gender or whatever in that sense, because I think, at least in the field such as medicine, most of the applicants are predominantly male. So you would guess it would develop that kind of bias.
That is exactly what happened. In 1988, the medical school was found guilty of racial and gender discrimination because of the use of this system. And it's worth pointing out, neither race nor gender were fed into the system. They didn't say this application is from a man, this application is from a woman. But what happened was the accepted applicants, particularly in the 1970s, were predominantly white and male. And the system was able to pick out other kinds of characteristics that were generally true of white male people, that were not true of female people or people who were not white, and in particular immigrant communities. So for example, it would classify people based on whether they had a female or male sounding name. It would classify people based on the neighborhood where they lived. And it was discriminating against immigrant-dominated neighborhoods. And to the hospital's credit, they were the people who brought this up. They did not mean to build an unfair system. And they were horrified when they figured out that this had happened. This is a very standard problem with supervised learning, where it's not going to find what you want it to find, it's going to find what you gave it in the training set. So if your training set has any kind of bias, whether it's based on gender, whether it's based on race, whether it's based on age, that is going to be reflected in the output of the algorithm. Even if you try to obfuscate it, even if you take out the characteristic that you don't want it to classify on. And before you say, well, this is the 70s and 80s, in 2018, Amazon was building an AI recruiting tool that worked in exactly the same way. It reviewed resumes, and it would forward to people resumes that they thought were potentially good Amazon employees, and it would reject everyone else without a person looking at it. And it identified predominantly female colleges and predominantly female sports. And it would downgrade people, for example, for playing volleyball. Not that that has anything to do with your coding ability, but it does have to do with the fact that most people who work at Amazon, in particular in technical positions, are male, and most of them don't play volleyball. And Amazon, to their credit, caught this before it ever went into effect, but they were never able to fix it. They weren't ever able to find a way to make this automated system not discriminate against women. So this is something to keep in mind. Your algorithm's results will reflect your data set, not what you wanted it to do. All right, and this is my saddest example. This is AI killing someone. So in Tempe, Arizona, last year, there was the first self-driving car accident that killed a pedestrian. We'd had other incidents where the driver had been killed, but this was the first time someone outside the car died. What happened was it was nighttime. A woman with a bicycle was crossing this road outside of a crosswalk, and there was a self-driving vehicle with a safety driver inside, but it was in the self-driving mode that was approaching. And the vehicle recognized that there was something in its way 6 seconds before it struck the pedestrian. It didn't know what it was, and it got really confused. It didn't know if it was a bicycle or a car or a person. A little bit more than a second before impact, it recognized that there was a person and that an emergency braking maneuver was required. And I'm going to quote directly from the National Transportation Safety Board report for the incident. Emergency braking maneuvers are not enabled while the vehicle is under computer control to reduce the potential for erratic vehicle behavior. The vehicle operator is relied on to intervene and take action. The system is not designed to alert the operator. So the computer knew that it had to stop. It had no ability to stop. It had no ability to alert the operator. The operator was looking at a screen in the car during this period and didn't see the person until less than a second before impact, didn't hit the brakes until after the person had already been struck. So what happened here? There are a number of critiques we can make of the actual AI algorithm, should it have recognized a person sooner or not. But the major critique is of the AI system. This system cannot drive a car. This system cannot brake if something unexpected comes into the road, which if anyone, I assume people here drive cars, it doesn't happen that often, but it definitely happens, whether it's a pothole, whether it's a tire, whether it's an animal, whether it's a child. There are occasions when you have to slam on the brakes. And hopefully you've been trained in how to do that. I was when I took driver's education. If you don't know how to slam on the brakes, you don't know how to drive a car. It's not the hardest skill involved. Now imagine that you're a human being sitting in this car. Imagine that you've been driving it for 20 minutes. Or rather, it's driving itself for 20 minutes, and it does everything. It controls its distance from other cars. It stops at lights. It stops at stop signs. It obeys the speed limit. It makes its own turns. It's navigating itself. You've driven this thing for hours, and it does everything by itself. A human being who can do everything that we're describing in terms of driving a car knows how to slam on the brakes. You will never find a human driver who hasn't figured out how the brakes work if they can also parallel park. But computers make that mistake. And so what happened, one of two things, either the human driver did not understand that they had to be paying attention at all times because the car couldn't stop, or possibly they were just struggling with task switching, which is a known issue in automated systems. People are not good at taking over from computers quickly. This is actually a critique that was the focus of a Federal Aviation Administration notice to operators, where they said to airlines, to people who commercially fly people around, reduce your use of auto-flight systems, which is the technical name for an autopilot, because excessive use of autoflight, it degrades the pilot's ability to fly the plane, and it also reduces their ability to respond quickly to an emergency. So people can't do this. We can't trade off easily with computers in time-sensitive applications like driving or flying a plane. And this is why some operators like Google, they actually don't have steering wheels at all in their self-driving vehicles. They say, if we can't do it 100% automated, we're not going to do it. Because this is a very serious problem with very dire consequences. So when do things go wrong? Things go wrong essentially when humans trust computers too much. And there's a tendency to do that. There's a view in the general population, hopefully not in this room anymore, that computers are unbiased and computers are smart. And if an algorithm is doing it, then it's going to be doing it in a smarter way than fallible people. And that's not necessarily true. Algorithms break all the time. And if you don't understand how it's working, you should not trust it. Things break when humans don't understand their role in the system. When they don't understand that they are there as a backstop for the computer. When they don't understand that they're not supposed to be trusting the computer, they're supposed to be interacting with it. So if you have a system that requires humans to be a backstop to a computer, you have to force their participation. You can't let them check out and think about something else or check their email. They have to be, required to pay attention. And that's a system design issue, because people by default will just sort of check out when they're not asked to think about things constantly. And finally, I think we just lost the monitor. Could you, yeah. Uh-oh. Oh, and well, I remember what the slide said. They fail when the failure states are not well considered. So for example, with the self-driving car example, they were considering a state where you don't want the self-driving system to be just constantly tapping the brakes. It makes for a very jerky ride. But they weren't considering what was going to happen in a true emergency situation when that system can't hit the brakes and when a human being might not be paying attention. So consider the system and consider the consequences. Because again, we're not playing checkers anymore. Now we're doing real things. Okay, yes. The second part? Yes. Well, an example is the self-driving car example. Mm-hmm. It varies. It depends on the particular application. So for the self-driving car example, they expected the human being to be fully in control of the car at all times and fully aware of their surroundings at all times. That was the system design. The person sitting in the car was not acting like that was their role. If you've watched the YouTube videos of people who are asleep while their cars sort of drive themselves down the highway, they do not understand their role in that system. Do not go to sleep in your car as it drives down the highway. Your car will drive into things in unexpected ways. Similarly, with the admissions example, people, they didn't understand that they weren't training it to find good doctors. They were just training it to match applications to older applications. So they abdicated the human role in that process, and they just trusted the computer when they shouldn't have. It mostly comes down to trusting the computer when you shouldn't. You need to make sure that it's absolutely trustworthy, which is a very hard thing to do. All right, so thus ends the depressing portion of the talk. It may not sound like it, but I'm actually an AI optimist. That's why I work in this field. I really do believe that computers working with people can enrich our lives and make our lives better in many, many ways. So how do we make sure that that's what's going to happen? Well, step one is to make sure that when a human is required to cooperate with a computer in an interactive system, they understand the system well enough that they can predict its behavior. So again, this is not requiring you to do a deep dive into optimization algorithms. It's the level of understanding we developed with the checkers example. So you need to have a high-level knowledge of how it's behaving under different circumstances, and you need to be able to figure out the kinds of mistakes that it's going to make. Now I have to remember what the second one was. It had to do with, it still had to do with, people take responsibility for your computer's actions. And the last one was you need to understand the failure states and make sure that they are appropriately mitigated. So I am not saying that we shouldn't use AI. I'm not saying that we should banish AI to only low-stakes applications. We should be using AI in industry. We should be using AI in medicine, but we just need to pursue a couple of extra steps. Oh, it's back. What was the second bullet? Okay, that was, when does it break? Okay, predict. Oh, there's a clear separation of responsibility between humans and computers. So this is just, you know what the computer's responsible for, you know what the human's responsible for. In terms of systems design, there should be as little overlap in those roles as possible, because again, humans are really bad at rapid task switching. Okay, here we go. Here's starting with the fun examples. Who's flying the airplane? So this is an F-16. The F-16 is a very interesting fighter jet in that it was the first mass-produced aircraft which is aerodynamically unstable. So what that means is in most aircraft, if you just let go of the controls, it'll sort of level out and fly itself. That's not what happens with an F-16. It will behave in unexpected and undesirable ways if you abdicate responsibility. You actually want that in a fighter jet because aerodynamic stability also decreases maneuverability. So they want this thing to be able to flip over and climb and do all kinds of crazy things when it needs to. And because of that, they sacrificed a degree of stability. What it also means is that no human can fly this airplane. So the responsiveness to the flight surfaces is so high, and that response changes with altitude and it changes with speed. You cannot hold in your head enough information to be able to control this thing just using rudder pedals and a control stick like you could older aircraft. So what they did was they built a partnership between a human and a computer, actually 4 quadruplex computers, because getting back to failure states, if the computer goes down, no one's flying the plane anymore. So what the human does is they decide which direction they want the plane to point. So they give sort of directional inputs. They decide this is where I want it to go, and then the computer decides how you're going to get there. And this has led to the expression among F-16 pilots that you don't fly the F-16, it flies you. And so this is everything that we were hoping for from a human-computer partnership, which is that the person is able to predict what the computer is going to do. The airplane is going to go the direction they're trying to point it with sufficient training. There's a very clear separation of responsibility. The person is deciding what the aircraft is going to do, and the computer is deciding how the aircraft is going to do it. And finally, they thought through the failure states. It is a very, very bad day if you are flying this aircraft without any computer control. So they put a lot of thought into not just how the computer controls work, but the kind of redundancy in the control system itself, so that failures are very rare. So this is the kind of partnership that you want to see. All right, and since I was brought here by my company, this is a product that was made by Beyond Limits. So it's an operations advisor for oil refineries. So oil refineries are enormously complex. You can think of it as a chemistry set that spans multiple football fields and that is running potentially millions of gallons of material per day. Everything is connected. Everything is running continuously. You can't hit pause while you try to figure out what's going on. And somehow human beings have managed to run these things for decades. So what can a computer bring to the table in an oil refinery? Well, it can bring the fact that it can pay attention to a lot of things at once. It can look at every single sensor in the oil refinery almost simultaneously, which a human can't do. It can have a perfect recall for how the refinery is supposed to be working, or at least how people think the refinery is supposed to be working. And it can constantly compare these things against each other because it never gets bored or goes to sleep. And so it can report back to operators and say, we think that there's an opportunity to improve the functioning of your oil refinery, to put it in a more profitable state. Here's what we suggest that you do. And one of the things that Beyond Limits does is we provide full audit trails for all of our recommendations in human interpretable language. So no black box models. We say exactly why we think you should do everything we recommend. And it's also able to diagnose problems with the plan itself. Plans are created by people, and they are imperfect. They're based on models that are imperfect. Conditions are changing. Sometimes people just overlook something. And that's one of the reasons why the Beyond Limits advisor does not run the refinery itself. It's always interfacing through people because we know that its knowledge is wrong. We know that it's not good at anticipating what you should do under novel conditions. But what it can do is help people to focus on the most important thing at any given moment in time. It can bring together all the information that you need, and hopefully none of the information that you don't, so you're not sifting through thousands of sensor time histories to try and diagnose a fault. You can look at the 5 most important things to understand. And you can rapidly make modifications to the system, or rather, chemical engineers can make rapid modifications to the system. You don't want your statistician running your oil refinery. And it's explicitly a partnership. There's nothing in here that allows the human being to just sort of abdicate responsibility to the computer. We're able to allow humans to be creative, to respond to novel situations, and we're able to use the computer to basically automate a lot of fairly routine tasks and interact with that person in a positive way. All right, so since very nearly everybody in the room wants to deploy AI systems, in addition to answering the 3 questions, this is what I would ask you to do. Don't trust computers. Verify that they're doing what you think they're doing, that they're going to do what you ask them to do, and understand it well enough that you can anticipate where they're going to make mistakes. Secondly, think about the system, not just the algorithm. It's really easy to calculate a precision and recall or an ROC curve and say, oh, look, my algorithm has really great area under the curve and all that. And it doesn't matter if deploying that system in the real world is not going to be successful. Like a 99% accuracy isn't necessarily good if a 1% false alarm rate is just constantly bothering operators, or it's causing people to get medical procedures that they don't need, or it's causing people not to get medical procedures they do need. So always think of how this is going to work in the real world, not just how it's going to work in the lab. And finally, make sure the system helps people. I feel very strongly that data scientists, engineers, people who work in this field should take responsibility for the systems that we built. And that we're doing this typically because we want to make the world better. And so just make sure that whatever you're doing, you're making the world a better place for people, not just computers, because computers don't have feelings yet. The last thing I'd like to say is that when people talk about AI, when they talk about automation, I think that we don't focus enough on how amazing the human brain is, how versatile, how successful and how valuable that it is today, and it's going to continue to be. We're not just trying to shove humans out of the way and have computers do everything. We don't give people enough credit. In particular, we don't give people who know an area, but not necessarily AI, enough credit. So this is a story about Chinook. Remember, Chinook was originally developed to dominate all humans in checkers, so that Canadian AI scientists could feel good about themselves. And this is, or was called, a 100-year checkers problem. So if you subscribe to checkers periodicals, they will have things like this, and they'll say, this is your board position, white is to play, who's going to win with perfect play? And this specific example was debated for 100 years, between about 1800 and 1900, and humans eventually decided that white would win in this position, that with perfect play, this was a win for white. There was a checkers grandmaster who did not program computers, was not an AI scientist, but he was aware of the Chinook project, and he was aware of the endgame database. And he said, you know what? People really do think that this is a win for white, but Chinook would know for sure, because Chinook has played every single possible move with this set of pieces. And so 100 years after this problem was solved by humans, it was actually solved by Chinook. And Chinook said, no, it's not a win, it's a draw. And when human experts went back and they looked at the line of play Chinook came up with, they said, that's crazy. It's no one would have anticipated. There were sort of counterintuitive moves and some sacrifices that had to be made. And so a person who, you know, again, not an AI scientist, not a computer scientist, but an expert in checkers was able to use this program to do something it had never been designed to do, and to solve a problem that humans had not been able to solve. So make sure that as you're integrating people into your AI systems, don't view them as a burden. Don't view them as something in the way. People are you know, amazing. And putting people together with computers is enabling things that we could not have imagined even 10 years ago. So with that, thank you so much.